And so now we'll look at the change of variables or change of coordinates formula for a multivariable integral. This is Theorem 10.58. So if omega is a set in Rn, and we'll take it to be an open set, just for technical reasons, whatever. We won't actually use that hypothesis explicitly because I'm not giving you that explicit of a proof, or really that formal of a proof. But we're going to have some change of variables given by u. So u is a transformation of Rn to Rn that transforms omega into some maybe simpler set. And this is needs to be a differentiable map on omega. So in other words, the derivative exists at every point x of omega. And then we're going to have our scalar valued function that we're integrating. So f is going to be a function from on the image of omega under u. So that's the coordinate transformed one, and it's scalar valued. So its outputs are real numbers. Then what we have is that the integral over the image of omega of f, and so we'll give it a dummy variable of integration x, so f of x dx. This is the integral over omega of f of u of x times, and then we have the absolute value of the Jacobian determinant times dx. And so you can think of this part here as being du. And so if this is f of u, then we can rewrite this sort of according to the standard mnemonic as the integral of f du, or maybe f of u du. There we go. Okay, so how do we prove this guy? So this is an analysis proof, so you start by fixing epsilon. So for a fixed positive epsilon, let's look at a point in omega, and let b be an element of the covering of size epsilon containing x. Okay, so we find a box that contains x. Okay. Then f of y is approximately equal to f of u of x everywhere on this little box, because we've picked our box to be big enough, right? So the difference between the max value of f and the min value of f on this little box is going to be no bigger than epsilon. Okay, so also, if we look at x plus omega, so what I'm doing here is I'm translating the set by omega. So this is all of the points x plus y where y runs through omega. So in other words, if this is my omega and this is my x, then I'm looking at taking this set and translating it like that. So this blue one here is x plus omega. I've just shifted every point in omega by x. Okay. Then for this guy here, since it's just a simple translation, the volume of x plus omega is equal to the volume of omega. All I've done is moved it. I haven't actually changed its size. So then the if I look at the volume of u applied to b, then this is the volume of u applied to B and then shifted by some fixed vector u of x. And then by our different derivative approximation, this is approximately equal to the volume of u prime x applied to B. And then that one is, by our previous results, the magnitude of the Jacobian determinant times the volume of B. And so then collecting this across all boxes, we have that the sum of, and then f evaluated at some point, y times volume of the image of bk under u is going to be approximately equal then to the sum of f at u of xk times the determinant of u prime x times the volume of bk, where here I'm writing yk for uxk. And then taking the limit as epsilon goes to 0, that approximation becomes an equality. And so that's how it works. So I've swept a bunch of details under the rug, especially about how the limits work out. But hey, this is a linear algebra class, not an analysis class. So what do you want? That's it for Math 306. Thanks for watching.